Okay, so this lecture is primarily an examples lecture, and we're going to use a gas turbine, and the reason we're going to use a gas turbine is we've already looked at it using the first law, so we can compare how we would use the first law to the steady flow energy equation to solve energy problems. So previous lecture we defined the steady flow energy equation using a control volume, it's a rate equation, and the only things we assumed was the flow is steady and the fluid is inviscid. And the inviscid assumption made our convection terms much easier to deal with. And then we made some simplifications to show you how you would apply this to simple bits of engineering plant. So we're going to cover how a jet engine operates and how it's slightly different to a stationary gas turbine. It's a nice example of using steady flow energy equation and force momentum equation together, and then we're going to sort of look at it compared to Brayton cycles. Okay, so what's different about a jet engine compared to a gas turbine? In effect, it's the two things on the ends, so the diffuser and the nozzle. And one of the things that the stationary gas turbine is designed to do is to generate power, which means a design imperative is to make sure that the turbine generates much more power than it needs to power the compressor, because that extra power goes to generating electricity. In a jet engine, effectively what you want is the turbine to be as small as possible. In fact, as small that all it does is power the compressor. And what you want to create is lots of excess enthalpy at the exit of the turbine, because this is used to go through a nozzle and produce thrust for the aircraft. Okay, so for the steady flow energy equation, what we're going to do is effectively take control volumes for each of these sections, and then you can work out the energy balances and the energy flow all the way along this jet engine. So you sort of solve it sequentially. You can also use the force momentum equation to look at the performance of a jet engine, and effectively what you do here is you draw a control volume around the whole thing, and then you do a force balance on this, and you've got your momentum flowing in and your momentum flowing out, and the difference in those two momentum flows generates a force on the control volume, and that force on the control volume is effectively the thrust that is generated by the jet engine, and this is what we're after if we're going to design a jet engine. So in a stationary gas turbine, the inflow momentum is zero, but in a jet engine, effectively the jet engine is moving with the speed of the aircraft through still fluid. So what we do is we change the frame of reference, and we say that the air momentum coming into the control volume has some momentum, and so therefore the net thrust that we generate is a function of these two things. Okay, and if we're interested in how much power we can generate from the jet engine, that's the force times the velocity. So the velocity is the speed of the aircraft, so that gives us this, and we're interested, or we could be interested in the efficiency of a jet engine, and that's just going to be what the useful stuff, what we want, the power, divided by the rate at which we're burning fuel. So this is the amount of thermal energy that's being created by burning the fuel. And we did this for a stationary gas turbine using the first law, if you remember. So we can also do this for the steady flow energy equation. And what we'll find out is jet engines are horribly inefficient. So how do we look at what's the comparison between closed cycle and open cycles? So closed cycle is effectively when we're using a system. So when we did this in term one, we said we had a little sort of cube of fluid, and it was at a certain temperature and pressure. Then it moves through the compressor, gets to state 2, higher pressure, and then it goes through to state 3, so it's higher pressure and higher temperature, goes through to state 4, so it loses its pressure and its temperature, we dump some energy back to the environment, and we kind of go around again. So this is the kind of the Lagrangian way of doing energy conservation using the system. We take a little mass of air and we kind of follow it around this system. And we look at the energy transfers, and based on these energy transfers we can work out the efficiency of our cycle. And we can do that effectively by drawing a big system boundary around the whole thing. You have work transfer going in, heat transfer going in, network coming out. So this is the network. So this is turbine generates lots of work. Some of it is used by the compressor, and what's left is used for useful stuff, and we reject some energy. Okay, and we have to do that because it's has to obey the first and the second law. Yeah. So the reason that's difficult for a jet engine is that we don't have any kind of recycled air going around a loop here. So the air coming in here is cold air moving at a certain velocity, goes through all of this stuff, and comes out of the exhaust again with a different velocity, kinetic energy, and a different temperature. And we can't handle the fact that the kinetic energy going in and the kinetic energy going out are different using the system basis, because the system basis doesn't describe kinetic energy because it's a system. Okay, so this is a good example of why control volume techniques are much more useful, and there's no reason why you couldn't use a control volume technique to do this system stationary gas turbine. And one of the features of a gas turbine is that effectively you get some compression for free because you use a diffuser. So although it's not sketched very well here, effectively with a diffuser you have an inlet here, and then you expand the fluid and the pressure rises in the diffuser, so you get some pressure rise for free before you put it through the compressor. So typically a jet engine will operate on a higher pressure ratio than a stationary Brayton cycle. So what does the jet engine open cycle look like? So effectively we get 6 stages. So we go from 1 to 2, which is our compression in our diffuser, and then we do our power stroke in the compressor to get us up to 3. And then we have to add all of the energy up to state 4, which is the entry to the turbine. And then we take out energy from the fluid going through the turbine, and we only take out sufficient energy from the fluid to power the compressor. That's all we want to do with the jet engine. And then this energy from 5 to 6 is us converting enthalpy to kinetic energy through a nozzle, and this the state of the fluid at 6 generates the useful thrust. Okay, so if you remember when we looked at stationary gas turbines, we could improve the efficiency by using intercoolers and reheaters, and we could recover a lot of the energy injected using regenerators. And obviously we can't do this in a gas turbine because they need to be small and light. So we really do have to burn all of this fuel, and all of this excess enthalpy we have to squirt out the back of a jet engine to generate the thrust that we're after. Okay, so we don't necessarily go from 6 to 1 here. We just go to here and then it goes around again. So it's kind of an open cycle. And how do we do this? So we covered this in the previous lecture. So just to sort of reiterate this, we've got 1 nozzle and 1 diffuser. So for instance, if we're after the nozzle, then we neglect the kinetic energy here, but the kinetic energy on the outlet is the thing that we're after. So therefore we've got a steady flow energy equation simplifies to this. So we covered this in the previous lecture. we need to deal with the compressor and the turbine. So these are sort of reflections of each other. The compressor, you add energy, and the turbine, you take it away. And this governing equation for the steady flow energy equation is typically this for a compressor and a turbine. And finally, we've got one burner. So here we can assume that there's no work being done, the potential kinetic energies are negligible, and the heat transfer effectively changes the temperature. So the pressure doesn't really change on a combustion burner in a jet turbine. So you end up with something like this. So the idea with the jet engine is you apply control volumes on the different sections all the way through, and you can track the temperature or the enthalpy of the gas as it goes through from section to section to section. So the interesting thing about a jet engine is how poor it is from an efficiency point of view. So when you generate the efficiencies, your jet engine efficiency is 20 odd percent. So this means only 1 kilo of the 5 kilos of fuel that you burn actually generates thrust. The rest is kind of squirted out the back of the jet engine. Doesn't really do very much. Most of this is down to the excess enthalpy. So this is because you're squirting high temperature gas out the back of the nozzle, and if you could squirt cold gas out the back of the nozzle, you could increase the efficiency by a factor of 3. So this kind of really covers a typical example of how to do a steady flow energy equation calculation. So we've looked at how a Brayton cycle can be used using a steady flow energy equation. We've shown how you can work out efficiency on energy rate budgets in the same way that you did it for energy budgets for the first law. And this concludes our lectures on steady flow energy equations.